Hard water is water that has high mineral content. Hard water is formed when water percolates through deposits of calcium and magnesium-containing minerals such as limestone, chalk and dolomite. Hard drinking water is generally not harmful to one's health, but can pose serious problems in industrial settings, where water hardness is monitored to avoid costly breakdowns in boilers, cooling towers, and other equipment that handles water. In domestic settings, hard water is often indicated by a lack of suds formation when soap is agitated in water, and by the formation of limescale in kettles and water heaters. Wherever water hardness is a concern, water softening is commonly used to reduce hard water's adverse effects. Sources of hardness. Water's hardness is determined by the concentration of multivalent cations in the water. Multivalent cations are cations with a charge greater than 1+. Usually, the cations have the charge of 2+. Common cations found in hard water include Ca2+ and Mg2+. These ions enter a water supply by leaching from minerals within an aquifer. Common calcium-containing minerals are calcite and gypsum. A common magnesium mineral is dolomite. Rainwater and distilled water are soft, because they contain few ions. The following equilibrium reaction describes the dissolving and formation of calcium carbonatia, CaCO3 plus CO2 plus H2O or Ca2 plus 2HCO3. The reaction can go in either direction. Rain containing dissolved carbon dioxide can react with calcium carbonate and carry calcium ions away with it. The calcium carbonate may be redeposited as calcite as the carbon dioxide is lost to atmosphere, sometimes forming stalactites and stalagmites. Calcium and magnesium ions can sometimes be removed by water softeners. Temporary hardness. Temporary hardness is a type of water hardness caused by the presence of dissolved bicarbonate minerals. When dissolved, these minerals yield calcium and magnesium cations and carbonate and bicarbonate anions. The presence of the metal cations makes the water hard. However, unlike the permanent hardness caused by sulfate and chloride compounds, this temporary hardness can be reduced either by boiling the water, or by the addition of lime through the softening process of lime softening. Boiling promotes the formation of carbonate from the bicarbonate and precipitates calcium carbonate out of solution, leaving water that is softer upon cooling. Permanent hardness. Permanent hardness is hardness that cannot be removed by boiling. When this is the case, it is usually caused by the presence of calcium sulfate and/or magnesium sulfates in the water, which do not precipitate out as the temperature increases. Ions causing permanent hardness of water can be removed using a water softener, or ion exchange column. Total permanent hardness equals calcium hardness plus magnesium hardness. The calcium and magnesium hardness is the concentration of calcium and magnesium ions expressed as equivalent of calcium carbonate. Total permanent water hardness expressed as equivalent of CaCO3 can be calculated with the following formula. Total permanent hardness equals 2.5, Ca2 plus 4.1, Mg2 plus. Effects of hard water. With hard water, soap solutions form a white precipitate instead of producing lather, because the 2+ ions destroy the surfactant properties of the soap by forming a solid precipitate. A major component of such scum is calcium stearate, which arises from sodium stearate, the main component of soap, 2C17H35COO plus Ca2 plus a 2Ca. Hardness can thus be defined as the soap-consuming capacity of a water sample, or the capacity of precipitation of soap as a characteristic property of water that prevents the lathering of soap. Synthetic detergents do not form such scums. Hard water also forms deposits that clog plumbing. These deposits, called scale, are composed mainly of calcium carbonate, magnesium hydroxide II, and calcium sulfate. Calcium and magnesium carbonates tend to be deposited as off-white solids on the inside surfaces of pipes and heat exchangers. This precipitation is principally caused by thermal decomposition of bicarbonate ions but also happens in cases where the carbonate ion is at saturation concentration. The resulting buildup of scale restricts the flow of water in pipes. In boilers, the deposits impair the flow of heat into water, reducing the heating efficiency and allowing the metal boiler components to overheat. In a pressurized system, this overheating can lead to failure of the boiler. The damage caused by calcium carbonate deposits varies on the crystalline form, for example, calcite or aragonite. The presence of ions in an electrolyte, in this case, hard water, can also lead to galvanic corrosion, in which one metal will preferentially corrode when in contact with another type of metal, when both are in contact with an electrolyte. The softening of hard water by ion exchange does not increase its corrosivity per se. Similarly, where lead plumbing is in use, softened water does not substantially increase plumbo solvency. In swimming pools, hard water is manifested by a turbid, or cloudy, appearance to the water. Calcium and magnesium hydroxides are both soluble in water. The solubility of the hydroxides of the alkaline earth metals to which calcium and magnesium belong increases moving down the column. Aqueous solutions of these metal hydroxides absorb carbon dioxide from the air, forming the insoluble carbonates, giving rise to the turbidity. This often results from the alkalinity being excessively high. Hence, a common solution to the problem is to, while maintaining the chlorine concentration at the proper level, raise the acidity by the addition of hydrochloric acid, the optimum value being in the range of 7.2 to 7.6. Softening. It is often desirable to soften hard water. Most detergents contain ingredients that counteract the effects of hard water on the surfactants. For this reason, water softening is often unnecessary. Where softening is practiced, it is often recommended to soften only the water sent to domestic hot water systems so as to prevent or delay inefficiencies and damage due to scale formation in water heaters. A common method for water softening involves the use of ion exchange resins, which replace ions like Ca2+ by twice the number of monocations such as sodium or potassium ions. Washing soda is easily obtained and has long been used as a water softener for domestic laundry, in conjunction with the usual soap or detergent. Health considerations. The World Health Organization says that there does not appear to be any convincing evidence that water hardness causes adverse health effects in humans. In fact, the United States National Research Council has found that hard water can actually serve as a dietary supplement for calcium and magnesium. Some studies have shown a weak inverse relationship between water hardness and cardiovascular disease in men, up to a level of 170 mg calcium carbonate per liter of water. The World Health Organization has reviewed the evidence and concluded the data was inadequate to allow for a recommendation for a level of hardness. Recommendations have been made for the maximum and minimum levels of calcium and magnesium in drinking water, and a total hardness expressed as the sum of the calcium and magnesium concentrations of 2 euro for a ml. Other studies have shown weak correlations between cardiovascular health and water hardness. Some studies correlate domestic hard water usage with increased eczema in children. The Softened Water Eczema Trial, a multicenter randomized controlled trial of ion exchange softeners for treating childhood eczema, was undertaken in 2008. However, no meaningful difference in symptom relief was found between children with access to a home water softener and those without. Measurement. Hardness can be quantified by instrumental analysis. The total water hardness is the sum of the molar concentrations of Ca2+ and Mg2+, in mole per liter or mol units. Although water hardness usually measures only the total concentrations of calcium and magnesium, iron, aluminium, and manganese can also be present at elevated levels in some locations. The presence of iron characteristically confers a brownish color to the calcification, instead of white. Water hardness is often not expressed as a molar concentration, but rather in various units, such as degrees of general hardness, German degrees, parts per million, grains per gallon, English degrees, or French degrees. The table below shows conversion factors between the various units. The various alternative units represent an equivalent mass of calcium oxide or calcium carbonate that, when dissolved in a unit volume of pure water, would result in the same total molar concentration of Mg2+ and Ca2+. The different conversion factors arise from the fact that equivalent masses of calcium oxide and calcium carbonates differ, and that different mass and volume units are used. The units are as follows: parts per million is usually defined as 1 mg per liter Ca-CO3. It is equivalent to milligram per liter without chemical compound specified, and to American degree. Grains per gallon is defined as 1 grain of calcium carbonate per US gallon, or 17.118 ppm. A mol is equivalent to 100.09 mg per liter Ca-CO3 or 40.08 mg per liter Ca2+. A degree of general hardness is defined as 10 mg per liter Ca0 or 17.848 ppm. A Clark degree or English degrees is defined as 1 grain of Ca-CO3 per imperial gallon of water, equivalent to 14.254 ppm. A French degree is defined as 10 mg per liter Ca-CO3, equivalent to 10 ppm. Hard-soft classification, because it is the precise mixture of minerals dissolved in the water, together with the water's pH and temperature, that determine the behavior of the hardness. A single number scale does not adequately describe hardness. However, the United States Geological Survey uses the following classification into hard and soft water. Seawater is considered to be very hard due to various dissolved salts. Typically seawater's hardness is in the range of 66-30 ppm. On the contrary, fresh water has hardness in the range of 15 to 375 ppm. Indices. Several indices are used to describe the behavior of calcium carbonate in water, oil, or gas mixtures. Langley saturation index. The Langley saturation index is a calculated number used to predict the calcium carbonate stability of water. It indicates whether the water will precipitate, dissolve, or be in equilibrium with calcium carbonate. In 1936, Wilfrid Langley developed a method for predicting the pH at which water is saturated in calcium carbonate. The Lsi is expressed as the difference between the actual system pH and the saturation pH. Lsi equals penthouse APHS. For Lsi greater than 0, water is supersaturated and tends to precipitate a scale layer of Ca-CO3. For Lsi equals 0, water is saturated with Ca-CO3. A scale layer of Ca-CO3 is neither precipitated nor dissolved. For Lsi less than 0, water is undersaturated and tends to dissolve solid Ca-CO3. If the actual pH of the water is below the calculated saturation pH, the Lsi is negative and the water has a very limited scaling potential. If the actual pH exceeds pHs, the Lsi is positive, and being supersaturated with Ca-CO3, the water has a tendency to form scale. At increasing positive index values, the scaling potential increases. In practice, water with an Lsi between -0.5 and +0.5 will not display enhanced mineral dissolving or scale forming properties. Water with an Lsi below -0.5 tends to exhibit noticeably increased dissolving abilities, while water with an Lsi above +0.5 tends to exhibit noticeably increased scale-forming properties. It is also worth noting that the Lsi is temperature sensitive. The Lsi becomes more positive as the water temperature increases. This has particular implications in situations where well water is used. The temperature of the water when it first exits the well is often significantly lower than the temperature inside the building served by the well or at the laboratory where the Lsi measurement is made. This increase in temperature can cause scaling, especially in cases such as hot water heaters. Conversely, systems that reduce water temperature will have less scaling. Water analysis, pH equals 7.5, TDS equals 320 mg per liter. Calcium equals 150 mg per liter as Ca-CO3, alkalinity equals 34 mg per liter as Ca-CO3. Lsi formula, Lsi equals pH, PHS, PHS equals where, A equals /10 equals 0.15, B equals -13.12 x log 10, OC plus 273. Plus 34.55 equals 2.09 at 25 a degree Celsius and 1.09 at 82 a degree Celsius. C equals log 10, Ca2 plus as Ca-CO3, 0.4 equals 1.78, D equals log 10, alkalinity is Ca-CO3, equals 1.53. Resistability index. The resistability index uses a database of scale thickness measurements in municipal water systems to predict the effect of water chemistry. Resisaturation index was developed from empirical observations of corrosion rates and film formation in steel mains. It is defined as RSI equals 2 phs a euro pH, for 6, 5, RSI less than 7 water is considered to be approximately at saturation equilibrium with calcium carbonate, for RSI greater than 8 water is undersaturated and, therefore, would tend to dissolve any existing solid Ca-CO3, for RSI less than 6, 5 water tends to be scale-forming. Percolates scaling index. The Percolates scaling index uses slightly different parameters to quantify the relationship between the saturation state of the water and the amount of limescale deposited. Other indices include the Larson-Skold index, the Stiff-Davis index, and the Oddo-Thomson index. Regional information. The hardness of local water supplies depends on the source of water. Water in streams flowing over volcanic rocks will be soft, while water from boreholes drilled into porous rock is normally very hard. Hard water in Australia. Analysis of water hardness in major Australian cities by the Australian Water Association shows a range from very soft to very hard. Total hardness levels of calcium carbonate in ppm are: Canberra 40. Melbourne, 10 a euro 26. Sydney, 39.4 a euro 60.1. Perth, 29 a euro 226. Brisbane, 100. Adelaide, 134 a euro 148. Hobart, 5.8 a euro 34.4. Darwin, 31. Hard water in Canada. Prairie provinces contain high quantities of calcium and magnesium, often as dolomite, which are readily soluble in the groundwater that contains high concentrations of the trapped carbon dioxide from the last glaciation. In these parts of Canada, the total hardness in ppm of calcium carbonate equivalent frequently exceeds 200 ppm, if groundwater is the only source of potable water. The West Coast, by contrast, has unusually soft water, derived mainly from mountain lakes fed by glaciers and snowmelt. Some typical values are: Montreal 116 ppm, Calgary 165 ppm, Regina 496 ppm, Saskatoon 160 to 180 ppm, Winnipeg 77 ppm, Toronto 121 ppm, Vancouver less than 3 ppm, Charlottetown, PEI 140 a euro 150 ppm, Waterloo Region 400 ppm, Guelph 460 ppm. Hard water in England and Wales. Information from the British Drinking Water Inspectorate shows that drinking water in England is generally considered to be very hard, with most areas of England, particularly east of a line between the Severn and Tees estuaries, exhibiting above 200 ppm for the calcium carbonate equivalent. Water in London, for example, is mostly obtained from the River Thames and River Lee, both of which derive significant proportion of their dry weather flow from springs in limestone and chalk aquifers. Wales, Devon, Cornwall and parts of northwest England are softer water areas, and range from 0 to 200 ppm. In the brewing industry in England and Wales, water is often deliberately hardened with gypsum in the process of Burtonisation. Generally, water is mostly hard in urban areas of England where soft water sources are unavailable. A number of cities built water supply sources in the 18th century as the Industrial Revolution and urban population burgeoned. Manchester was a notable such city in northwest England, and its wealthy corporation built a number of reservoirs at Thirlmere and Habswater in the Lake District to the north. There is no exposure to limestone or chalk in their headwaters, and consequently the water quality in Manchester is rated as very soft. Similarly, tap water in Birmingham is also soft as it is sourced from the Elan Valley reservoirs in Wales. Hard water in the United States. More than 85% of American homes have hard water. The softest waters occur in parts of the New England, South Atlantic Gulf, Pacific Northwest, and Hawaii regions. Moderately hard waters are common in many of the rivers of the Tennessee, Great Lakes, and Alaska regions. Hard and very hard waters are found in some of the streams in most of the regions throughout the country. The hardest waters are in streams in Texas, New Mexico, Kansas, Arizona, and Southern California. See also: carbonate hardness, DGH, water softener, water quality, water treatment, water purification. References: ABC World Health Organization Hardness in Drinking Water, 2003, A.B. Herman Wenger Currency RTNER, Water in Ullman's Encyclopedia of Industrial Chemistry, 2006, December, Wiley Euro VCH, Weinheim doi, 10.1002/143567A28001, Christian Nitsch, Hans Joachim Heitland, Horst Marson, Hans Joachim Sler 1/4 Usler, Cleansing Agents in Ullmann Euro Unregistered Trademark S Encyclopedia of Industrial Chemistry 2005, Wiley Euro VCH, Weinheim doi. 10.1002/143567A07137, Lime softening. Retrieved November 4, 2011. Wisconsin DNR, Carbonate Chemistry, Stephen Lower. Hard water and water softening. Retrieved October 8, 2007. P.P. Kuezi. Scale reduction and scale modification effects induced by ZN. Retrieved March 29, 2010. Sogg, Thomas J. Schock, Michael R. Lytle, Darren. Ion exchange softening, effects on metal concentrations. Journal AWWA 91, 85 Euro 97. ISNA 1551-8833. Drinking water hardness calcium magnesium scale stain laundry. Water-research.net. Retrieved January 26, 2013. Francia Echo 3/4 EC Health Significance of Drinking Water Calcium and Magnesium, February 2003, Pocock S.J., Shaper A.G., Packham R.F. Studies of Water Quality and Cardiovascular Disease in the United Kingdom. Psi. Total Environ 18, 25 Euro 34 doi, 10.1016 per second 0048-9697, 81, 80047-2. PMIDA 7233165. Mark S., Jackman Gaddy H., Dartigues J.F., Comminges D. Cardiovascular Mortality and Calcium and Magnesium in Drinking Water, an Ecological Study in Elderly People. J. Epidemal. 18, 305 Euro 9 doi, 10.1023 per hour, 1,023,618,728,056. PMIDA 12,803,370. Robenowitz E., Axelson G., Rylander R. Magnesium and calcium in drinking water and death from acute myocardial infarction in women. Epidemiology 10, 31 Euro 6 doi, 10.1097/0001648-199,901,000-00007. PMIDA 9,888,277. McNally N.J., Williams H.C., Phillips Drive, Smallman Rayner M., Lewis S., Venner, Britton J. Atopic eczema and domestic water hardness. The Lancet 352, 527 Euro 531 doi, 10.1016 per second 0140-6736, 98, 01402-0. PMIDA 9,716,057. Miyake Y., Yokoyama T., Urea, Kiem, Shimizaki. Ecological Association of Water Hardness with Prevalence of Childhood Atopic Dermatitis in a Japanese Urban Area. Environ Res 94, 33 Euro 7 doi, 10.1016 per second 0013-9351, 03, 00068-9. PMIDA 14,643,284. Arnido Penna, Valido Blasco J., Puig Barbara J., Arturo Severa, Campus Crew or plus or minus is JB, Pax Armister, Villamara Enval ZQUEZJL, Feliz Dauda C. Domestic water hardness and prevalence of atopic eczema in Castlin school children. Salud Publica de Mar Copyright Zico 492, 295 a €301 doi, 10.1590 per second 0036-3634200700400009. PMIDA 17710278 a multicenter randomized controlled trial of ion exchange water softeners for the treatment of eczema in children, protocol for the softened water eczema trial http www.set-trial.co.uk/. Definitions of units of measure for water hardness, USGS water quality information, water hardness and alkalinity, total water hardness, corrosion by water, T.E., Larson and A. V. Skold, Laboratory Studies Relating Mineral Quality of Water to Corrosion of Steel and Cast Iron, 1958 Illinois State Water Survey, Champaign, Illinois pp. 43, €46, L. ISWSC 71, Stiff, J.R., H.A., Davis, L.E., A Method for Predicting the Tendency of Oil Field Water to Deposit Calcium Carbonate, PET. Trans. AIME 195. 213. Oddo, J.E., Thompson, M.B., Scale Control, Prediction and Treatment or How Companies Evaluate a Scaling Problem and What They Do Wrong, Corrosion/92, Paper No. 34. KK, Act 2 AGL, Dishwashers and Water Hardness, Melbourne Water Public Health Compliance Report July-September 2006, Sydney Typical Drinking Water Analysis, Perth Drinking Water Quality Annual Report 2005-06, Brisbane Drinking Water, Adelaide Water Quality, Hobart Drinking Water Quality, Darwin Water Quality, Ville de Montre Copyright Al, Lo de Montre Copyright L. Ville Montreal QC Car. January 22, 2013. Retrieved January 26, 2013 A, Canadian Water Quality Association. File, Current Sites 2011 Water Hardness Canada Inc. HTML, 12013-309 and 35 seconds AM Water Hardness Total Households Canadian Cities. Retrieved October 4, 2013 A, Frequently Asked Questions. Saskatoon Car. Retrieved January 26, 2013 A, 2006 Winnipeg Drinking Water Quality Test Results, City of Toronto, Toronto Water FAQ, GVRD Wash Smarter Water Facts, City of Charlottetown Water and Sewer Utility Water Report 2006. aquasafecanada.com. Retrieved January 26, 2013 A, Region of Waterloo Residential Water Softener Performance Study Testing Report No. April 1, 2011. Region of Waterloo Car. Retrieved January 26, 2013 A, Table 2 Drinking Water Hardness. United Utilities. Retrieved March 3, 2012 A, AB Drinking Water Quality. United Utilities. Retrieved March 3, 2012 A, 7 Trent Water B11 dB. 7 Trent Water. Retrieved March 3, 2012 A, Bristol Water Hardness Level. Bristol Water. Retrieved March 3, 2012 A, Southern Water SO14 Area. Southern Water. Retrieved March 3, 2012 A, EC1A7B Water Quality in Your Area. Thames Water. Retrieved March 3, 2012 A, dwi.gov.uk, anglianwater.co.uk, Wilson, Amber. Parrott, Kathleen. Ross, Blake. Household Water Quality Water Hardness. Retrieved April 26, 2009 A, Briggs, J.C., and Fick, J.F. Quality of Rivers of the United States, 1975 Water Year, based on the National Stream Quality Accounting Network, U.S. Geological Survey Open File Report 78-200, 436p. External links, AXO Nobel, Langley Saturation Index Calculator, Water Hardness Unit Converter, Converter for Hardness of Water.